Welcome to part 2 of our peptide sequencing tutorial. So a brief reminder of what we did last time is we take a peptide like this. This is a truncated peptide at its third residue. We put it into the gas phase. We heat it up with collisions with small molecules like argon gas or nitrogen gas. Our proton mobilizes like this. Can go anywhere and it bounces around, and wherever it stops, a bond breaks. And we talked about the essence of CID being that bond breaking, and then the separation of these two, in this case a B ion and a neutral. Now, you can also show a B ion like this, and why it's shown like this sometimes you'll run across it with the carbon monoxide sticking off one end, is that it's pretty easy to see that if you heat it up a little bit further, charge moves, off goes carbon monoxide as a neutral loss, and now you have what's called an A ion. Again, declarative knowledge is something to remember. Now, I've shown the B ions like this, very simplified, but you'll see them in textbooks a lot like this. There's going to be a nucleophilic attack by an adjacent carbonyl. It will form a cycle. Look, I'm just going back and forth. That oxygen just binds to this carbon and everything then is in a ring. Watch the double bond move, and now you have the fabled oxazolone ion, or B ion that's in oxazolone. Okay? Now at this point, it gets interesting. Look at our neutral. Our neutral can very often still be hydrogen bound to its B ion, so it hasn't fallen out. It's not gone yet. And what it can do is, we're just going to move this charge. It's just a formality to move it from here to here and back and forth. This neutral can do a nucleophilic attack. This nitrogen has a lone pair after all. Zoink! Pull off that proton. And now we have a Y ion. So when you break it in amide, you get a B ion on the N-terminal side and a Y ion on the C-terminal side. And mechanistically, this is good enough for me that you think of it this way. Again, I provide you with some background reading, and there's some 40 or 50 pages that you can read if you want to know more about this. There's a lot going on in terms of rearrangements in the gas phase, but this gets it for now. So what have we learned? We're only talking about singly charged for now. It'll be easy to move on, but to generalize this. But B ions, their mass to charge ratio is equal to the residue masses plus 1. Now, you've been taught to subtract a proton during deconvolution, even though technically this doesn't have a proton, but it doesn't, whatever. But the point is, you've been taught to subtract a proton, and so the deconvoluted mass is, you're going to subtract 1, and so it's going to be equal to the sum of the residue masses, and that's easy. Okay, so a B ion is the sum of the residue masses. Very cool. Now, that's its mass, not its M over Z. Its M over Z is one more than that. Now remember, always think, am I in M over Z or am I in mass? And don't make the mistake of between those two domains. Know which one you're in. Now singly charged Y ions, they equal the M over Z of all, their M over Z equals all the residue masses plus 18. That gives you back your water plus 1 proton, and that was put there during ionization. So you're going to subtract this proton when you deconvolute, like say something's 1,000 M over Z, and it's a plus 1, you're going to assume that it got a proton during ionization, and you're going to say, well, it weighed 999 outside of my mass spectrometer. Now we're going back to earlier lectures. So the deconvoluted mass of a Y ion is the sum of the residue masses plus water. The B ions, deconvoluted mass, is the sum of the residue masses. We said that already. Y ions are really just peptides. They're just like peptides. Now, if you add the deconvoluted masses of a B ion and Y ion, this doesn't work in the M over Z domain, it equals the peptide's mass. So that's great. Simple. Now, if you add the M over Z's of the Y ion and the B ions and then subtract 1, it will equal the M over Z of the singly charged peptide. Now, that seems weird, almost like it violates the law of conservation of matter. That's not the case. It doesn't. Go back to the mechanism and look how these are formed, and it may or may not make sense. So just remember it. But in any case, because this can be complicated, it's better to deconvolute your data before you deal with it, I find. And when we do now, we're going to be working with this table of residue masses. We're going to work with a lot, and we're going to start sequencing peptides.